Maybe you have stopped because the camera is looking all this. Thank you at all for staying here. Also, the people that is in this house, maybe. For us, it's a pleasure that Professor Ide-san is with us after a very long trip from some days to arrive to Japan here, but he, like other 5 or 6 times ago, is with us sharing his acknowledgement. Professor Ide-san is professor of Tokyo University, and during the last years, maybe 2 decades, he is continuously working in a very novel topics like is the slow earthquakes. He has conducted the most important research in this topic. Also, he has the lead of a big project in Japan, the slow to fast earthquake. And during all this period, he has maintained a connection with us, with the Chile, with the University of Chile. We are some students, some Chilean students, and for this reason, he has visited several times. Then we are very happy that Professor Ide is with us. Thank you for all of the years that the chair of you are acknowledging it. Thank you.
Buenos días. Soy Satoshi Ide, profesor de Universidad de Tokio. Yo quiero hablar español, pero español no es bueno, no es suficiente para hacer esta presentación. Lo siento. Pero mi inglés no es muy bien. Pero so I will start presentation in English, but I try to implement as possible. Okay, so the title is Physics of Fast and Slow Earthquakes. As already introduced by Sergio, this is a fairly new topic in our seismology or earthquake science. So for public, we always explain what is slow earthquake using this kind of cartoon. So we know earthquake occur in country like Japan or Chile in this kind of system, subduction zone. One plate is subducting below the other plate, and once the energy accumulation is become very big, this part of plate interface broken and earthquake occur. There is slip motion in the plate interface that radiates from the shaking and sometimes makes tsunami. But this is what we know about earthquake. And around 2000, 20 or 25 years ago, we discovered similar but very different phenomena called slow earthquakes. That is similar in the sense that is slip movement of this plate interface. The different thing is it's slip very slowly. And for ordinary earthquake, even if it is very large earthquake, the duration of this kind of phenomena is up to several minutes. cannot be tens of minutes. But for slow earthquake, the slip continues for second or minutes, day or months or even years. So it can continue for very long time. That is a big difference. So all movement occurs slowly. So there is no strong shaking or no tsunamis. But so we can think, so this kind of phenomena is not so dangerous because there's no shaking or no tsunamis. However, it can be a problem. And recently in Japan, this kind of slow earthquake, or one of the name of slow earthquake, slow slip event, is broadcasted even in daily news. This is ordinary news in Japan, national TV news. Last year, last March, we had a slow slip event nearby Tokyo. Here is Tokyo, and slow slip event occurs somewhere here, and also some earthquake, small, not actually small. Some earthquake makes minor disaster, just an economic disaster for some restricted area. But this small, medium class earthquake occur because of slow slip event around here. Or more in detail, official GSI, this is a Japanese Institute for Geodesy. They determine the slip area for this event around here. Tokyo is here. So it makes some kind of social interest or some people worry about what happened because of this. And it is explained that plate interface moves slowly. This is a actual movie shown in this news program. So many people start to think this is an important phenomena to monitor, to understand earthquake phenomena generally. And there is also another problem. In Japan, we expect very large earthquake, real threat for our life, especially in Western Japan, called Nankai earthquake. And for Nankai earthquake or Nankai trough earthquake, Japanese government have some special system to make extra information. There is not earthquake prediction, but it's kind of warning to prepare, just prepare to check your status about anti-shaking. That is to check, not construction, but the location of furniture or preparation of evacuation material such as water or so that kind of basic system, not so much. You don't have to evacuate to somewhere, but you can check about the status of if something large earthquake happened, you can prepare well. But anyway, it's very confusing system. Many people think this is a kind of earthquake prediction. So it was also broadcasted globally. In many countries, this is the first released last year. Last year, 2024. Yes, it's not correct. 2024. And it was broadcasted in many countries. And the important thing is this Nankai trough earthquake extra information can be released based on the activity of slow earthquake, not ordinary earthquake. So if something very strange, we cannot tell what is actually that. But if we observe something very strange in slow earthquake activity, this information will be released, and that makes some impact in society. And also, slow earthquake is very popular it's not just Japan. Slow earthquake has been observed in these countries. Yeah, mainly around Pacific Ocean, southern Pacific area. And probably we have some observation of slow earthquake in Chile. And this is a paper published this year by Sergio. And in this paper, we report some slow earthquakes actually observed in this area. These purple symbols means the location of slow earthquake in Chile. So it's a common problem for all these countries. So it's worth to investigate this apparently not so dangerous event. Today I want to show these things. First, I want to introduce what is actually slow earthquake. Slow earthquake has various aspects. So as much as possible, I want to explain what are these events. And the second part will be how we understand this event. Basically, following one scaling law. Scaling law is what connects small scale phenomena with large scale phenomena. So using mainly we talk about this scaling law in the second part. And if I have time, maybe I don't have time, but if I have time, I will talk something about the difference between fast and slow earthquake in the final part. Okay, let me start from the introduction. Yeah, maybe we start from the why we are now observing this kind of phenomena, starting from the discovery. We observe this, yeah, as I explained, this kind of phenomena has been detected for 20 or 25 years. But it started from the Kobe earthquake in Japan, 1995, 30 years ago. In Japan, there is a very large, it's not large in the moment magnitude, it's just magnitude 7 earthquake, but below the Japanese big city, Kobe city. Because of this earthquake, that's for Japanese society, it was very big event. And we studied Kobe earthquake, but 30 years ago, here is a Kobe area, and this is 100-kilometer circle. In Japan, we had such seismic network system. It was, at that time, we thought it's not so bad. But actually, it was not so good, even at that time, compared to other countries in the world. So Japanese government understand earthquake research is very important in Japan. So they introduced many stations, and 5 years, 10 years from this time, we had such, it is just a part of seismic station in Japan. This is 1995, this is 2005. These are just high sensitivity or strong motion station, but in reality, we have several thousand seismic stations down in Japan. And also we have GPS, a geodetic instrument in Japan. So that's big difference. It's occurred because of the Kobe earthquake. And these are seismic network, and we have GPS network. Using this GPS network, we can monitor the deformation of Japanese island very in detail. This is a already very old movie. It was made 25 years ago. That shows how Japanese island deformed. This is a animation made by real record, but the displacement is magnified by 2 million. 2 million. So it's exaggerated, of course. But the sense, you can understand the sense of deformation. So Japanese island is pushed east-west in this direction because Pacific plate is subducting from here to here. And also Western Japan is shrinking north-south direction because Philippine Sea plate is subducting from the south. Because of this subduction, Japanese island is deformed. And most of this deformation in the Tohoku area have been released in 2011, big earthquake, magnitude 9 earthquake. But magnitude 9 earthquake occurred because Japanese island deformed in this way, and it went back into 2011. So we expect something similar will happen in Western Japan. That is a Nankai earthquake I told at the beginning of this talk. So it's quite obvious Japanese island is deforming and also accumulating some energy, strain energy. But during this kind of observation, we found this deformation in Western Japan sometimes reverse. And this is a GPS record around this area. All these stations usually move to northwest direction. So it is, if we plot it in eastward displacement, always it goes to this way. Yeah. But sometimes it reverses like this. So maybe five hours, once in 7 years, the movement is become opposite to the usual direction. This is the timing of slow slip event, first discovered in this area. And we can determine where is the area of slip deformation. And in 1997 and 2003, here and here, we can estimate the slip area like this. And the slip area is very similar. And something similar happens many times in this area. That is so-called Bungo channel slow slip event. The first slow slip event discovered in subduction zone. This is the first discovery of 1999. This is Bungo channel, the same as the slow slip event I explained. And after the discovery, many slow slip event was discovered in Japan and also in many other subduction zones in Cascadia, Mexico, New Zealand, Costa Rica, now in Chile, and in many places, similar slow slip event has been observed. And once we can determine the slip area, we can measure the size, of course, size, and also how much stress is released by this slow slip event by comparing earthquake size measured by seismic moment with fault area. In this kind of classic comparison, all earthquake, or we can say first event earthquake, are located around here, but slow earthquake are always located very differently. So the stress change, the change of stress during event is, it's a 10 or 100 kilopascal. This number will be compared later with style. But this stress drop is much by 2 orders smaller than ordinary stress change of large first earthquake or simply earthquake. So these are shear slip event. Shear slip. So it's a slip event. Generally, it's slip event. In that sense, it's similar to the earthquake. But the stress or energy change is very different. This. And soon after the discovery of slow slip event, we also discover slightly different phenomena, seismogenic phenomena. That's radiated seismic wave, very tiny seismic wave. It's called low frequency earthquake. So this is a comparison between earthquake distribution in Japan around the Kobe earthquake And this is 5 years, no, 10 years later. So the number, because we, yeah, as explained, we improved seismic observation system pretty much between these two periods. So the number of events increased 10 times. This is 1,000 events per year. This is 100,000, 10,000. This is 10,000. This is 100,000 events per year. But this difference is not just the number of events. In this new observation system, we found qualitatively different phenomena. Qualitatively, what means qualitatively? These events are very, the appearance of these events are very different from ordinary earthquake. These are shaking record of earthquake for some medium-sized earthquake and small earthquake. You can see that the medium class earthquake is a little longer pulse than small earthquake. Because if earthquake become larger, the characteristic shaking period is longer. So usually medium or even larger earthquake has longer period than small earthquake. But if you compare, this is low frequency earthquake, newly observed event around here. This shaking period is similar to medium size, not like small size. Small size is more high frequency. And but if you compare amplitude, this amplitude is very small, less than 1 micron per second. Even smaller than small earthquake of magnitude 0. This is magnitude 0. So it's very small amplitude, but a long period. So that's what we don't observe before. So this is, and also these are located around here, Nankai region. This area is essentially the same as where slow earthquake, slow slip event occur. And almost the same time, we also observe so-called tectonic tremor. It is sometimes it's also called non-volcanic tremor, or etc. But this is a typical record of tectonic tremor. It is 5 minutes, 300 seconds, observed in several stations in this area. So you can see this is if you observe this at single station, you may think this is just noise. And it's actually very similar to noise, traffic noise, for example. If a train or a car in the highway, we observe those human-made noise, we can observe very similar signal. But if they are observed at many stations simultaneously, that means it comes from some deeper place. Cannot be on the surface. So we can determine the location around here. It's essentially the same as the location of this low frequency earthquake. And now we understand this is actually the continuous occurrence of low frequency earthquake. And this is 5 minutes, but it can continue even more longer time. This is 1 hour, 1 hour. And this is 24 hours, 1 day. So this tiny shake, it's very tiny shake. Amplitude is just 0.1 micron per second. So we cannot feel it. But a very good seismometer can detect this event. And it can continue for very long time, successfully, like this, intermittently. And now we can monitor the occurrence of this kind of tectonic tremor, automatically. So this is when the result of monitoring tremor occurring in this area. So this movie shows the location of tremor for when tremor occurs, it is shown by red color, and it changes to blue and disappear. So you can see tremor occur, and this is plot, just a temporary is flowing plot, and it shows 30 days corresponding to this color. So you can see tremor occur around here almost every day. And if you look at this for a long time, you see sometimes it's, there is some typical pattern. That is a migration of tremor source. So tremor starts somewhere and propagate to some other one direction or bilaterally. So it's it's very complicated occurrence. But generally, they occur almost the same place, restricted in this gray area. And so far, we look at these in map view. But if we take cross section like this, A and A dash, we can locate those tremor or low frequency earthquake. These two things are now understood as the same phenomenon. Just tremor is just continuous occurrence of very small low frequency earthquake. So we can determine the location of low frequency earthquake in detail precisely. And if we locate low frequency earthquake along this cross section, we can see is that low frequency earthquake occur around here. And there is a lineation of earthquake here. We know those earthquakes are in the subducting slab, subducting plate. So this is inside plate, not plate interface. So plate interface must be shallower around here. So we interpret this low frequency earthquake occur on the plate interface here. And also between the continuously sliding deep plate interface and locked shallow plate interface. Between these locked and continuous slipping region, we observe low frequency earthquake. It is so kind of partially locked part of the plate interface. And we also determine the direction of slip, and we can confirm that this event occurs as the slipping motion of this on this subducting plate interface. In addition to low frequency earthquake and seismically observed low frequency earthquake or tectonic tremor, and geodetically observed slow slip event, we also find some intermediate scale events, so-called very low frequency earthquake. We already talked that tectonic tremor occur around here, and these are tectonic tremor records measured at several stations. Tectonic tremor is a high frequency seismic signal. High frequency means several hertz, 2 hertz or 8 hertz. These are typical frequency of tremor. But if we select different frequency range, in this case, frequency range is between 0.02 to 0.05, or in period, we can say it is between 20 seconds and 50 seconds. Between these frequency range, we can observe impulsive pulse, also shown in this red lines. And this impulsive pulse is almost the same time with tremor record. So tremor and this kind of impulsive pulse are simultaneously observed in many places. And we can determine the location and also slip direction. And all these observations suggest these are different observation of very similar phenomena. Always they are observed almost the same place, same time. So we see at least 3 different phenomena simultaneously. The one is seismic high frequency tectonic tremor. And this is medium scale, very low frequency earthquake, and very low frequency over geodetically observed slow slip period. And this slow earthquake, so these are slow earthquake. The major phenomena, these 3 things, tectonic tremor and very low frequency earthquake and slow slip events. And they are very interesting in several characteristics. The occurrence of tectonic tremor is characterized by some spatial region. It's not occur totally randomly. Rather, as this slide shows, this is time and the location of tremor for more than 10 years. So you can see tremor occurrence is nearly periodic. And they occur nearly the same time, not completely the same, but there is some pattern. Maybe the occurrence interval is about half year or 3 months. Or in some place, it's occur more continuously, almost every day. So these are spatial characteristics. So there is some location specific behavior of tectonic tremor. And as I already showed using a movie, the migration behavior is very typical for tremors. This is one example of tremor occurrence in 2006. This time, tectonic tremor shown by these red dots and very low frequency event shown by these orange circles. And slow slip event shown by these blue rectangles. Simultaneously occur from here to here. If we take a space and time plot, they propagate from here to here. This is tremor. This is about 2 weeks. Within 2 weeks, it starts around here and propagate to the east up to 200 kilometers. This is a very typical migration behavior. We can observe this kind of migration very frequently in this area. But the propagation occurs, but the propagation speed is very slow. It is about 100 kilometers in 10 days. It's actually the speed of turtle, 0.1 meter per second in standard unit. During this, sometimes if we grow up around here, general trend, migration trend is in this way, but sometimes it goes back, reverse movements sometimes occur. This reverse movement is about the speed of 5 meters per second, maybe something like bicycle, it's slow, but much faster than this speed. But these are, I said this is a little faster, but if we compare this earthquake rupture propagation speed, it is 3,000 meters. So even this movement is very slow compared to earthquake migration or earthquake rupture propagation. And also, yeah, we can observe very different, very wide, diverse phenomena about tremor migration. It changes between 0.1 meter per second to 10 meter per second. But yeah, several orders slower than fast earthquake. And sometimes we also observe continuous deceleration of migration. So this is time and space. So tremor migration starts relatively rapidly, but it is decelerated in parabolic way. We can assume this using parabolic curve like this. So this kind of parabolic migration is very typical for some diffusive physical process. So we may say this is diffusive migration. There's some study that compiled propagation speed with duration. And this study shows that propagation speed decreases if it continues long time. So this kind of deceleration. The slope is not exactly the parabolic, but we can expect that this kind of tremor include some diffusive physical process. That will be, I will mention it later again. And also another very interesting characteristic of slow earthquake is it is very well modulated earth type. Our Earth, planet, and also ocean is always deformed by the gravity by moon and sun. That is tidal stress. And there has been very long debate whether earthquake is controlled by tide. What we know is there is some statistically significant effect on earthquake by tide, but it is very difficult to detect. However, for slow earthquake, it's so obvious. Some tremor is very well controlled by tide. This is an extreme example in a part of Japan around here. Here we have tidal station. Tidal station measure just height of ocean. So these are tide record at these two stations. It's almost the same. And as you know, tide changes every day, basically twice. High tide, low tide, repeat twice a day. But during this tide change, tremor occur at this timing, the timing of low tide. This is just 20 days. If we continue this kind of observation for 10 years, about 10 years, we observe tremor at the timing of low tide. Almost all tremor occur just during low tide. This is because, there is no model. This is totally observation. Just observation of timing of tremor and observation of tidal level. So our interpretation is, this is because in this area, tremor occur, this is ocean, inland ocean in Japan. So this event occur under the sea, ocean. So when ocean mass, water mass is moved by tide, the pressure decreases, and the plate interface is likely to slip because the overriding pressure decreases. That is a basic mechanism, and it can be useful to explain the tremor occurrence, not just this place in many areas. So tremor is controlled by this kind of tidal stress. Tidal stress change is just usually 1 kilopascal. So it is very small, but not that different from the stress change of due to slow earthquake. The final, not final, but another characteristic of slow earthquake is energy. Yeah, I said seismic, slow earthquake is too slow, but it still radiates some seismic energy, seismic shaking, very tiny seismic shaking. So we can measure energy from seismic wave using seismic record. And this is an estimate of seismic energy from tremor. This is time and energy rate. And this is also seismic moment rate for the same event. As you can see, this is a measurement of seismic energy. This is a measurement of seismic moment. I didn't explain what is seismic moment today, but seismic moment is actually the static measure of earthquake. And seismic energy is dynamic measure of earthquake. So we can compare two different physical quantities, seismic energy and seismic moment. But as you can see, these are the shape are very similar or almost identical. So we can say tremor is always, tremor keeps seismic moment and seismic energy at the same rate, almost the same average rate. And this rate is called scaled energy, seismic energy divided by seismic moment. It is, there is some special name so-called scaled energy. And this energy is 10 to the minus 10. And we can also determine seismic energy from slow slip event using geodetic measurement and seismic measurement. And these are another group of people who measure scaled energy for slow slip event as all in the 10 to the minus 10. So 10 to the minus 10, always 10 to the minus 10. This is a kind of a efficiency as a seismic wave radiation phenomena. But for earthquake, real earthquake, it's more efficient. Seismic energy is much stronger. Usually it is 10 to the minus 5. 10 to the minus 5. Compared to first earthquake, we can say that slow earthquake is not at all efficient for seismic radiation. It is 10,000 times inefficient as in the aspect of seismic wave radiation. So these are all characteristics of slow earthquake I want to explain. Then, so we want to explain these phenomena using one interpretation, that using scaling law for slow earthquake. This is a comparison between slow and fast earthquake. What we know is there is only one common feature between fast and slow earthquake. That is a mechanism. Mechanism is both phenomena is shear slip on fold, planar plane. The size can be different. Earthquake can be very small, something like magnitude minus 10 earthquake actually possible. And from magnitude minus 10 to magnitude plus 10, that is earthquake. For slow earthquake, we have some difference in size. We have magnitude 0 is tremor or low frequency earthquake. Magnitude 4 is a medium size event called VLFE. Magnitude 7 is a slow slip event. These are, they have different names, but they are all in slow earthquake in different sizes. We already talked about the expansion speed is very slow to compare first earthquake. And also stress change is smaller by 2 orders. This difference is about 100 times. It's big, but if we compare with energy moment ratio, it is the difference is much bigger. 10,000 times difference between fast and slow. So these are so far I explained. We will talk about other characteristic about between slow and fast earthquake. Probably we cannot explain everything. It's already. So comparing tremor, LFE, and very low frequency earthquake, VLFE, and the slow slip event, we propose that they share the same relationship in this diagram. This diagram is between the size of phenomena measured in seismic moment or magnitude compared to simply duration, how long it continues. And in 2007, what we know is just tremor, LFE, VLFE, and many slow slip events are located around here. But he proposed that these are connected by this single line. This single line is a proportionality between seismic moment and duration. These two quantities are very well defined for ordinary regular earthquake. And this is the slope of 1/3. This is a very strong constraint for ordinary earthquake. All earthquake occur following this law, this rule. There is no earthquake falling around here or here. But slow earthquakes are located very differently and also represented by single line. So this is at that time, it was a kind of hypothesis. And actually, there is this is a update in 2014, but still there are very large gaps here and here. So there are many criticisms to this idea, especially. So this large gap was left for a long time after the proposal of this hypothesis. So there are many challenges to this idea. There are some people who suggested that there must be something missing between this slow earthquake line or fast earthquake and fast earthquake line, and they plotted some event. But these events are not earthquake. These are actually glacier earthquakes, earthquake in ice. So it's a totally different event. And after the search, we tried to look for some event falling between these two lines. But after 15 years, nobody found event in this area. Actually, as I showed in this map, this is a kind of our detection limit in seismology. So if we have something around here, it must be detected. It's not very difficult to detect something happening around here. And we are so seriously looked for event in this area, but we cannot find, nobody find it. So maybe we can conclude there is no event actually between this line and this line. And another group of people suggested that this line cannot continue to this way. It must turn, it must have kink and change to different line. It is the same line for fast earthquake. So this is another challenge by different group. And also there are some very different observation that slow slip event follows one third trend, like fast earthquake. This study was published in Nature, so it was very influential. But we found that their measurement have a very serious error. So and it is a strong artifact in this study. So we can disprove the result of this study. So this is not so important, but there are several things to consider. Anyway, the important thing is we have large gap around here and around here. So many people may think this hypothesis of a single relation may not be true. But after in recent years, especially in these 10 years, we've actually found what's happening around here. as already shown in this curve, our observation capacities, observation ability is not the same for all frequency range. This is a shape of seismic noise. And so far, we explained that we can observe tectonic tremor at high frequency and very low frequency earthquake in low frequency. So that kind of thing is demonstrated in this kind of spectrogram. This is spectrum for 1 day. And this is frequency from low frequency to high frequency. So we usually observe tremor at high frequency. And we can observe very low frequency signal around here. Between tremor and VLFE, what we observe is microseism. Microseism is noise made by oceanic wave. So this microseismic noise is very strong, and we cannot see anything between tremor range and VLFE range. This is spectrum. This is frequency and amplitude. We observe very low frequency signal around here and tremor signal around here. But between these two, we have very strong peak. This is microseismic. Microseismic is very well known in seismology. This is some standard noise model between period and amplitude. The microseism is strong around here, 5 seconds or 18 seconds. And around here, microseism is relatively smaller. This is for acceleration. So to be consistent with this observation, we need to deform this diagram like this. So we can observe around here. We can observe tremor around here. And here, because of this trough of noise, we can observe very low frequency event. So we can observe very low frequency event simply because noise is small, just in this range. So if noise is small, fortunately, we can observe something between tremor and very low frequency event. That is very difficult because this microseismic noise is very strong. The level is different by 100 times. So usually it's impossible. But then we have just one example of real observation of signal between VFE and tremor. That is observed by the best seismic observation. It is an ocean bottom borehole broadband seismometer, very expensive one. Ocean bottom borehole in key region, Nankai area. And also, tremor occur very close to this observation point. These are two boreholes. There are several boreholes. And tremor occur just 10 kilometers from this site. So it's very unusual observation. So we cannot observe, but even this area, usually, this is a similar spectrogram, time and frequency. You see these are microseism. Microseism become large or small depending on weather, actually. So, and we have many tectonic tremor observed in this area. And these are observation record of tremor. And we see this day tremor activity is very active. And also microseismic noise is very quiet. So this is just we are lucky to see all signal from low frequency to high frequency. This is from low frequency to high frequency. So usually we observe just this part as very low frequency event and this part as tectonic tremor. But if direct observation is possible, we can observe continuous signal from very low frequency to high frequency. This is noise level. Noise level signal is stronger than noise level. So this is a very clear evidence about the continuity of signal from this size to this size. And also we can, this is direct observation. We can also measure the strength of signal indirectly by stacking a lot of data. So by stacking a lot of event, we can also measure the amplitude level of signal between wave range and tremor range. And we confirm that the signal amplitude is continuously changing between two levels. So we are quite sure that signal actually exists between two frequency bands, but we cannot observe it in real nature. Maybe I can skip. So maybe this is a little too specific, so I can skip. And also, but maybe so. But the question is how we can interpret such broadband nature of record. We can find some similar physical phenomena in other field of physics. The very famous example is Balkhausen noise that is observed in ferromagnetic material like iron. The magnetic field changes. When magnetic field changes, there is some electric noise in the ion. This is time and electric noise. This noise is actually very similar to what we observe for tremor and low frequency earthquake. And this kind of phenomena is explained by some stochastic process. The very easy, this is a little complicated, but a very easy representation of stochastic process is just random process. We can assume status of some space, some plane changes just randomly, depending on the status of surrounding area. It is so-called cell automaton. So we can introduce some simple rule to change the status of each box cell to change slip or stop. And this is totally stochastic process. But using this, some simple rule, we can explain such, this type of rapidly fluctuating signal, and also, long continuous, areas, signal, long continuous area. And the slip pattern is changing like this. So this is a Brownian type explanation of throwers. So now we can understand that this part was divided in the previous scaling law, but it's actually continuous. So the same physical phenomena can be observed as high frequency event as low LFE, and also low frequency event as VLF. But it can be continuous, but although we cannot observe directly. And another gap is also around here. This part is recently considered as represented by different process called tremor cluster. We already explained the tremor migration occur like this. This is time and space, so tremor moves space and time. This movement has some group of tremors. So we can consider this group of event as single event. So this is a tremor cluster. And we have some different statistical law for the size distribution of tremor cluster, like earthquake size frequency statistic of Gutenberg-Richter law, but it's too specific, so I will skip. But the important thing is we have moment and duration scaling. And some people says, as I said, this trend might be changed to this way. Because if we plot tremor cluster, size of tremor cluster in this plot, this trend is not exactly this trend. It can be observed in different area in Nankai and Cascadia. But this is a result from one group. There are different results from different groups. Another group determine tremor cluster, but it's located around here, not in this line. This goes below this group. And also other group determine tremor size and located around here. So that kind of observation is sometimes occurs. So it looks this trend, but overall it goes to this line. Why this kind of thing happen? So actually, what we observe is this is what we explained. Real slow earthquake signal must be like this: high frequency fluctuation and low frequency continuous sleep. But what we can observe is just this noise. So everything is limited. And we recognize event as a part of this upper part that is over noise level. So and also, we have some thresholds in this diagram, moment and time diagram. What we can detect is just a part of some continuous distribution. We need to understand this. And also, if there is some limit in time measurement, we easily consider this part of events like this kind of trend. So that is the reason why we have such distribution, but sometimes we interpret like this different trend. So this is actually the current status of moment and duration scaling growth. It was very isolated in the previous diagram, but now we can say that this part is fueled by continuous phenomena. We may say this is broadband slow earthquake, continuing from this scale to this scale. And also this part is filled with many recent observations about tremor cluster and also slow sleep event. So we can understand that this moment and duration proportionality line is continuous from very small scale to large scale. And this is very different from first event. Of course, there is very strange first event. Sometimes first event can be very slow. So-called tsunami earthquake is a kind of slow earthquake. It was actually called slow earthquake 30 years ago. But these earthquakes are slightly shifted from first earthquake relationship. So still we don't see anything in this area. Recently, some people are proposing we can observe something around here. There's just a detection limit in seismology, but it's a bit too early to say really nothing for entire region. But we can say there is some area that cannot be filled by earthquake-like phenomena in this diagram. So first earthquake and slow earthquake behave very different. And also we need to understand, another thing we need to understand is that this part, there is no event. But that it doesn't mean nothing happened in this area. Actually, there might be something, and quite likely, because we cannot detect anything that falls in this area. So it's written as hidden. So in other words, what we can observe as slow earthquake scaling along this line is actually the upper limit or fastest slow earthquake we can observe. And many phenomena are probably just hidden, escape from our observation. I think it's almost time to finish my talk. So I think that final part can be skipped. So what is that? This is actually what I want to conclude. So far we said that the earthquake and the slow earthquake have very different scaling law, and the reason is probably earthquake and slow earthquake are governed by popular but different physical mechanisms. The first earthquake, we know, first earthquake is rock failure in the earth, and it propagates very fast with seismic waves. So as physical process, what is occurring around earthquake is fracture, and also seismic wave propagation, seismic wave radiation. And when earthquake occur, always fracture and seismic wave radiations are coupled. So seismic earthquake is physical process that is governed by wave equation. Generally, seismic wave radiation enhance fracture. So there is a coupling between fracture and seismic wave always. So it is seismic wave controlled phenomenon. But slow earthquake cannot propagate like that. There is very little seismic waves. So seismic wave cannot couple with fracture. So how fracture propagate? So fracture need to propagate in diffusional way. So it is controlled by diffusion equation. Diffusion equation and wave equations are, if you know physics very well, it's very similar, just the slight difference in time derivative. So, but these two processes very fundamental in physics. So there is one group of event controlled by wave equation, and another group of event controlled by diffusional deformation, diffusional process. And diffusional process can be very slow and also ubiquitous. And we know, in the Earth, there are many types of slow deformation actually happening. Not just about earthquake, maybe in volcano and in deep Earth, mantle convection is occurring. Those slow deformation is basically controlled by diffusional process. So diffusional process is much more popular in Earth's interior. So probably we see must exist a lot of different diverse phenomena in this hidden region. And slow earthquake phenomena must be very popular. And what we can observe is just a tip of iceberg. On the other hand, first earthquake is very special. It is controlled by this narrow range of scaling law. So my conclusion is that because we are seismologists, earthquake scientists, we are always think earthquake is normal. But as deformation inside the earth, earthquake is very abnormal, very rare, very strange phenomena controlled by unusual physical process, that is wave propagation. So it is special, and it is probably much more common. So the conclusion is, slow earthquake are ubiquitous, and the first earthquake is so special, rare things. That is, this is summary of today's talk. This is my last word I want to say. That's it. Thank you for your listening.
Thank you very much, Mr. Ilsan, for your talk. And we have time for some questions. Thank you.
Please. Thank you for your talk. I have a question when we compare slow earthquakes in subduction zones, like you have done with slow earthquakes in faults, let's say, for example, the San Andreas Fault or the North Anatolian Fault. I know that those kind of earthquakes were not part of your talk, but I was wondering if they follow the same scaling laws and the same physics in general, for instance.
Thank you. That's very interesting, important question. And yes, there are also slow earthquake. We can observe along San Andreas Fault, the Alpine Fault, maybe. These are slow earthquake occurring in very small scale, I would like to say. San Andreas Fault, slow earthquake is observed in just a very narrow band, maybe just 2 kilometer, 5 kilometer, very narrow band. Probably because of that, most slow earthquake along San Andreas Fault fall around here. So usually hidden region. But in near San Andreas Fault, we have very good observation. So our detection limit goes slightly in this direction. So we can plot San Andreas Fault phenomena around here. And we know that is slightly on the left of this law. And it is probably because in San Andreas Fault, the region of slow earthquake is very limited. Because of that, all these phenomena occur in smaller scale than subduction zone. That's my interpretation. But it's actually very important current topic to understand what's the real difference between subduction zone and transform fault. Thank you.
We have a question for online people, and which is the minimum magnitude that you can detect for the slow slip events, and if this minimum magnitude will be controlled by the GPS resolution.
Thank you. This is also a very important point. In this diagram, we can say it's actually not easy to define what is event, but the minimum duration of slow slip acceleration, maybe we can say slow slip acceleration, minimum duration of slow slip acceleration is about several hours, 2 to 3 hours. And the size of the moment magnitude is around 5. So something around here. So that is a minimum size of slow slip event, we may say. And that is the control that cannot be observed by GPS. That is only observed by geodetic instruments, strain meters. Strain meter and tilt meter, those geodetic instruments has a better, finer resolution than GPS. But it's also a bit tricky. The noise level is very high. So it's very difficult, still very difficult. But generally speaking, using geodetic measurement, strain meter and tilt meter, we can observe a little smaller slow slip than GPS.
Thank you. There is other question?
Thank you, Ide-san. Very wonderful talk. I know this is outside of tectonic earthquakes, but I'm wondering if you have any sense or intuition or expectation whether volcanic tremor and volcanic LFs and VLFs will also follow the same physical scaling laws or completely different processes.
Thank you. I totally skipped that point, but yes, I talked low frequency earthquake just as tectonic something. But in reality, we also observe similar phenomena around volcano. That is called volcanic low frequency earthquake, or more popular way it is called deep low period, long period event, DLP. There is a different name, but the same phenomenon. And that is also very common observation and very related to low frequency earthquake, probably. But in fact, the seismic wave signature is very different, actually. We can, for example, we can determine a focal mechanism of tectonic low frequency earthquake relatively well. And it is consistent with subduction motion. But in volcanic area, I think still nobody presented really understandable focal mechanism. Many people determine focal mechanism, but all results are different. And what we know is it includes large non-double coupled components, generally speaking. So it's very difficult to interpret what's actually making volcanic DLP or volcanic LFE. And the size limitation is also probably a problem. Tectonic slow slip events occur relatively wide area, several tens of kilometers. But volcanic LFE is much more concentrated. So probably we don't expect something around here for volcanic one. And all volcanic LFEs are located just around here. So it will be not easy to derive any scaling law for volcanic LFE. But it's still under, many people are seriously studying it. So I think that will, that kind of research is very important. We will see the answer in the future.
Okay.
Yeah.
And we have one last question. It's for an online person, and it's about magnetic change. But if there is some observation of magnetic change before or after and slow slip events.
Magnetic observation. Magnetic temporal observation. I don't know so well about that kind of observation. What we know about magnetic observation is magnetic observation is important to know about the location of geofluid, underground fluid. And I cannot say anything about temporary change, but spatial distribution is, there is some study about using magnetic observation to discuss spatial change of electronic, usually electronic, the changes, resistivity change underground. And some people say that we can detect some anomaly of resistivity, somewhere very close to slow earthquake. So we consider slow earthquake is very well related to geofluid, and that can be detectable by magnetic observation.
Thank you. Thank you very much. Thank you for your wonderful presentations. Please. And I have the opportunity to say that tomorrow at 4 o'clock, Professor Ide-san will do another talk about the predictability of earthquakes.
It will be, probably you expect something like hierarchical things, right? Predictability means.
Yes.
So I cannot say so much about prediction. But something I will talk something related to understanding words. Understanding words.
And do you remember the room?
That's in mine.
in my building that is in the same faculty. That's 4 o'clock.
Eduardo Simian.
Eduardo Simian auditorium. Please, we maybe some of you is interested, and tomorrow at other talk of Professor Ide. And thank you.